Okay, so today we're kind of taking a step back almost, and we are going to be using properties of isosceles and equilateral triangles. Largely, this will be done in an algebraic fashion, which we're all going to love. For some reason, we just don't like using algebra, but it's a skill that we need to work on. So, it should be an enjoyable experience. So, anyway, I can use the properties of isosceles triangles and I can use properties of equilateral triangles. That's our goal by the end of the day. And just as a quick review, isosceles triangles have at least two sides that are congruent, and equilateral have three sides and three angles that are congruent. The angles, of course, being 60 degrees each. Um, so, vocab terms: legs of an isosceles triangle, vertex angle, and base angles. So I put this picture in because I feel like it does a really good job explaining what each of these are. Um, the vertex angle is always opposite the base, and then the legs are the two sides of an isosceles triangle that are the same length. So 12 and 12 here are both the legs, and then our base is 9 units. And then the base angles are the two angles that connect to the base of the triangle. They're kind of self-explanatory once you get the hang of them, but it's helpful to have that picture to reference to start with. So I would try to make sure this picture ends up in your notes. Continuing on, so isosceles triangles, we have the isosceles triangle theorem, and what this says is if two sides of a triangle are congruent, then the angles opposite those sides are also congruent. So what this means is, so we have these two sides that are congruent here. We have side AC and side BC. What that tells us then is angles A and angle B are also congruent. And once again, there's a very drawn out trigonomical explanation for this. You'll learn about this thing called SOHCAHTOA, and it uses sines, cosines, all this other stuff that you can use to calculate those angles. We're not doing that this year, but it's just something that will be used going forward. Me personally, how I remember the opposite angles, I always think of them as, okay, so this side is opposite angle 1, this side is opposite angle 2, and then for the isosceles triangle theorem, we're not talking about that third one, but if we were, this side would be opposite that angle. So it's kind of, if you just draw that arrow straight across, it's going to be that one angle opposite it. So then the converse of the isosceles triangle theorem says, essentially, if the two angles are congruent, then the sides opposite of those angles are also congruent. So in this case, we have angle 2. The side straight across from it would be side DE. And then we have angle 1, which is straight across from side FE. So side FE and side DE are congruent to each other. Yeah. Pretty delightful stuff. So once again, these two are very important for today. Make sure they make their way into your notes. Continuing on, we'll see a lot of problems like this. A lot of problems like this. So they tell us, name two unmarked congruent angles. So if I look at this, I can say, oh, well, angle D and angle C are congruent. Those are already marked. So we have to find two more angles that are congruent to each other that are not already marked. And of course, we have to have justification for this. It's not asking for justification, but we would have to have that justification. So what I like to do first is to look at this and kind of figure out what sides I can say are congruent, and then we'll figure out what angles I can say are congruent. So right away, what I see is this side CB here is opposite angle D. And so I know that the side opposite angle C is also going to be congruent. So I want to label both of those right away, just because it's going to make my life easier down the road. So next step to me, what I notice is we have side DB. That was kind of sloppy. So we have side DB, side CB, and side BA are all the same, which means these individual triangles are actually going to be congruent to each other. So this blue triangle and then this green triangle are both going to be congruent to each other. Looking at this without doing any of that, we could have said, okay, angle C and angle A are going to be congruent, and they're both unmarked. And why that is because right off the bat, they had this line CB and line BA labeled as congruent. And if we look back to our Isosceles angle theorem, that tells us then that those two base angles must be congruent then as well. So we can use that to say angle C is congruent to angle A. Now there's another pair we could have chosen. We could have said angle CBD is congruent to angle CBA, which CBA is congruent to angle CBD. Now, that one would have taken a little bit more work, and if it asked us to explain, it would take a little more explanation, because we would have to say, okay, well, based on the Isosceles angle theorem or Isosceles triangle theorem, blah, 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 CPCTC, essentially these two triangles are congruent, which means their vertex angles must be congruent as well. So long story short, easy answer, angle C is congruent to angle A. Slightly harder but also correct answer is angle CBA is congruent to angle CBD. Continuing on, name two unmarked congruent segments. Okay, so now this is the piece where all that work we did back here comes in handy. So I'm just going to use this triangle that we already marked up, knowing that we need to find two congruent unmarked segments. And what I see is, since these triangles are congruent, then their bases must be congruent. So that being side CD and side CA are congruent based on, we could say the triangles are congruent by side angle side, and then CA is congruent to CD by CPCTC. Congruent parts, or corresponding parts, congruent triangles are congruent. Lovely, lovely stuff. So I would say CD is congruent to side CA. And let's just take a gander and see if there's any others that we could say. I think that's our only possible answer, actually, which is rare, but delightful all the same. So, which statement correctly names two congruent angles? Okay, so anytime we have a multiple choice question like this, instead of going in and labeling literally everything in the problem, what I like to do is I like to just go in and check each answer and work from there, because that's going to be the more efficient way to solve the problem. Now, that being said, you could go in and you could say each angle that's going to be congruent and then kind of solve it that way, but I just don't think it's wildly efficient. So I choose to do it this way. So PJM, so this angle right here, and the lines are already blue, so I don't know why I always choose to use blue. So this angle is congruent to PMJ. PMJ. Okay. They look congruent, but there's no markings that can prove to us that they are congruent. So I'm going to just put a little question mark by that one right now, because that might be the right answer, but since there's no markings, I'm guessing it's probably one of those trick answers that they like to throw at us. So we'll continue on. Angle JMK and angle JKM. Okay, so that angle and this angle. So once again, we have angles that look congruent, but we can't really tell for sure if they are. So now I know that this problem is just one of those tricky ones where they're trying to trick us, which that was really redundant. But so continuing on, KJP. So this top angle here and JKP. So JKP. Okay. So once again we have similar. Then let's look at PML and PLK. PML and PLK. Okay. So looking at this, those two angles look nothing alike. And quite frankly, they're the only ones that look nothing alike, which makes me start to wonder if something's fuzzy with this problem. So let me take a gander real quick. Okay. Yeah, so that one's not it. All right, let's reset because I think I've missed something here. So let's reset again. JMK. Okay. I see what's going on here. Okay. So let's take a look at option B real quick. So JMK, which is this bottom angle, and then JKM, which is this bottom angle. Okay, so I know these are congruent, and why I know that is because if we ignore all this garbage in the middle, that did a successful job of throwing me off. So if we ignore all that garbage, what we're left with is we have this one big isosceles triangle on the outside, which I outlined like an absolute preschooler. But if we look at this, so we have this side is the same as this side, which means that our two base angles must be the same, and our base angles are JMK and JKM. So we know that those are the same. Once again, going back to isosceles triangle theorem. That one was kind of tricky. That one threw me for a loop. So let's look at our next one here. Which statements correctly name two congruent sides? So once again, I like to do the same process. So JP and PL. JP, so this piece here, and PL, those don't even look the same. So I feel pretty confident saying prob's not. And then PM and PJ. PM and PJ, which They look pretty similar. So once again, I think this is going to be one of those tricky ones where they're trying to mess with us. I'm going to put a question mark next to it, but I'm fairly confident that's not it either based on the last question. Then we have JK and MK. So JK and MK, which I think we're getting closer, but I don't think that one's it either, even though they do look very similar. So I'll leave a question mark, and then I'm going to say prob not next to that one, because I don't think it's that one, but at the same point, it is kind of closer to what I'm thinking here. And then PM and PK. So PM, this piece here, and PK, this piece here. So I actually think this one's the answer we're looking for, because once again, if we look at this whole triangle here, highlighting it in black and highlighting it, you know, like a kindergartner still, we do have these two base angles that are the same, which means that these two legs must be the same based on the converse of Isosceles triangle theorem. So what the converse says is that if we have these two base angles that are the same, then the two legs must also be congruent. So I'm actually fairly confident this time that it is D. Now, continuing on, now we get into our equilateral triangles. So a triangle is equilateral if and only if it is equiangular. So for it to be equilateral, it has to have all the same angles as well, which I kind of hinted at back in 4.1 or 4.2. But essentially, if you have all the sides that are the same, all the angles must be the same too, and that's vice versa. So if each angle is the same, then each side is the same. If each side is the same, then each angle is the same. And of course, all the angles must be 60 degrees for equilateral or equiangular triangles. And then our 4.4 says each angle of an equilateral triangle also measures 60 degrees. So equilateral triangles are not wildly terrible. What is important to remember here, though, is sometimes we might be using these isosceles triangle theorems to prove that something is an equilateral triangle, which I know is counterintuitive, but we'll kind of get into more of why and how that happens in the next couple problems. So our first problem here, they tell us that we need to find the measure of angle R, and we need to find the length of PR. So let's focus on angle R first. Now, what I notice straight away is I notice we have two sides that are the same. So I know this is at least an isosceles and maybe an equilateral triangle. So what our isosceles triangle theorem says, or no, is it the converse that I'm talking about? I forget which one. So isosceles triangle theorem says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So going back to this problem, then I know if I draw my arrows straight across here, side or angle P and angle R must be congruent based on that isosceles triangle theorem. Now, I can solve for what each of these angles is right now, and I think that's going to be our best course of action. So let's go ahead and do that. So I know right away angle P and angle R are equal to each other. So I'm going to say angle P equals angle R. And then I also know that angle P plus angle R is going to equal 120 degrees. And why I know that is because angle P plus R plus Q is going to equal 180 degrees. So what I've essentially done is I've plugged in this 60 here for Q, and subtracted it from both sides to get to that 120. So if P and R are the same and added together they equal 120, I know I could substitute X in for each of those since they are the same, and I could say 2X equals 120. Solving this, I would say X equals 60, and X is equal to both P and R. So I know each of these angles is 60 degrees, and if each of the angles is 60 degrees, then all the sides are also the same, because that would be an equiangular triangle, which means it's equilateral. So for this problem, angle R, so the measure of angle R is equal to 60 degrees. And then we can also say line PR is equal to 5 centimeters. So just to recap what we did here, because I know we moved kind of quick on that. We started off with just knowing that these two sides were 5 centimeters. From there, we were able to say angle P and angle R were the same. And then we used that information to say, okay, P plus R plus Q is going to equal 180, because all the interior angles added up must equal 180. And then we knew P plus R would equal 120. And we knew P and R had to be the same. So we were able to say, okay, well, 60 plus 60 equals 120. So they must each be 60 degrees. And that's how we solved it. For the angle, that's how we solved it for the angle. And then once we figured out it was an equilateral triangle, we already had two side lengths that were 5, so we knew this final side length must be 5 as well. So it can get kind of confusing working through these isosceles rules to get to equilateral triangles, but it's one of those things where repetition is going to be key. And you'll see a lot of proofs. A lot of your proofs are going to be using these tools. So if we go back, I would make sure this is in my notes, this isosceles triangle theorem and converse of isosceles triangle theorem. Then I would also make sure these equilateral triangles are in my notes as well. Which, if you were to use these in a proof, you would just say definition of equilateral triangle. But so if it was a proof, you would just say definition of equilateral triangle. We'll just write that there for your own note-taking purposes. So let's continue on to our next examples. So they want us to find the measure of angle T. So once again, when I see this problem, I see, okay, we have two side lengths that are the same, which tells me, based on the isosceles triangle theorem, then angle T and angle S must also be congruent, which I know then, since angle S is 60, angle T is 60. And anytime I see two angles that are 60, I know this final angle is also going to be 60, which means this final side is 3.5. Anytime you see repeated 60s, it's a good sign that it's going to be an equilateral triangle, which typically just makes life so much easier. All right, couple problems left to work through. So, this is our same triangle that we just talked about. So once again, they want us to find the side length of TS, which, like we said last time, these two sides are 3.5, which means these two angles are the same, which means both of them are 60, and of course 60 plus 60. So if angle T plus angle S plus angle R equals 180, because they always have to equal 180 because all the angles inside a triangle add up to equal 180 100% of the time. We do a little substituting. We say 60 plus angle R equals 180. Then we solve that out and we find out that angle R equals 60, which means we have an equilateral triangle, which means all the sides are the same, which of course means side TS is 3.5. Delightful. Lovely. Delightful. Love it. So we need to find the value of each variable in this equation. Now, this equation, or this example is a little bit more difficult. Now, I don't say it's more difficult because of algebra. That does play an effect. But since they give us no actual real angle measures, it does become a little more challenging. So I'm just going to show you what I would highlight first. The first thing I notice right off the bat is angle E and angle F are the same. So me knowing my Isosceles triangle theorem and the converse of the Isosceles triangle theorem tells me right off the bat, if these two angles are the same, F and E, then these two sides, DF and DE, must also be the same. So right off the bat, I can tell this is an equilateral triangle. All three sides are the same, which means all three angles are the same. So finding the values of the variables can be a little bit more challenging, but now that we know it's an equilateral triangle, it makes it a lot easier. So what I mean by that is I know, let's deal with the angles first. I know each individual angle is going to be 60 degrees. So I'm going to say 4x minus 8 is going to equal 60. Now I could also say 4x minus 8 plus 4x minus 8 plus 4x minus 8 equals 180 degrees. But to me, that's just making my life more difficult for no realistic gain. So since I know each angle is 60, I'm going to use that fact to my advantage. Now, to solve this, I'm going to add 8 to both sides, and I'm left with 4x equals 68, and I'm going to divide each side by 4, which is going to leave me with x equals, I believe, 17. 17 times 2 would be 17 times 2 would be 34 plus, yeah. So x equals 17, which is awesome. And if I were to plug that in, I would get each angle being, of course, 60 degrees. Now, the more challenging part, in my opinion, would be finding these side lengths. But once again, it's not wildly terrible. So I have two different side lengths here. And by that I mean I have two different algebraic representations of side lengths. I know that they equal each other, which makes my job not wildly terrible. So I'm going to say in blue, I'm going to set these two equal to each other because I know each of those side lengths has to be the same. So I'm going to say 6y plus 3. And I'm going to hit the next page button because why not? Equals 8y minus 5. Now I'm going to go through and solve this equation. So I'm going to add 5 to both sides. And I'm going to subtract 6y from both sides. And I'm left with 2y equals 8, which means y equals 4. Which is lovely and delightful because that's all they wanted from me. They wanted me to find the value of each variable. Now, if I needed to find the measurement for everything, I could then take this 4 equals y or y equals 4, and I could plug it back into either of these equations. And if I did that, I would find out that each side length is 27 units, which once again, you don't have to do that in this problem, but I'm just trying to prepare you for when you inevitably are asked to do exactly that. Going on to our final question, they say find the value for each variable. So once again, well, not once again, this one, in my opinion, is a little bit easier because right away I see we have 3 sides that are the same length, which tells me, of course, that we have an equilateral triangle, which once again means this equals this, and 3x for each of my individual angle measures here is going to equal 60. So I'm going to start off by doing the angle measures again. Knowing 3x equals 60 makes my life just a cakewalk, so I divide each side by 3. We finish our one-step equation and we say x equals 20. Oh my goodness, we're halfway there, just like that. So next thing I need to do, I need to say, okay, 2y minus 6 is going to equal 8 because both of those sides are congruent to each other because all the sides are congruent in an equilateral triangle. So I'm going to set up that equation, 8 equals 2y minus 6. Then I'm going to solve this. Now, this, of course, is a 2-step equation, which just makes it like a 7 on the difficulty scale. So I'm left with 14 equals 2y, divide each side by 2, and we have y equals 7. So we now have our x and our y variable, which means we're done, which is lovely. If you have any questions on this, it's a lot of problem solving stuff, which I have the utmost faith in all of you. My number one recommendation would be try not to be scared of it. I know when we see algebra, a lot of the times we kind of go, uh-oh,